From broken glass to a $2 billion empire, how is foam glass dominating the glass recycling industry? Millions of tons of glass are discarded every year, taking millions of years to decompose. But instead of landfilling, a groundbreaking technology has transformed these sharp pieces of waste into foam glass, a super lightweight, fire-resistant, and perfectly insulated material that is taking the global construction industry by storm. So what miraculous process transforms old, worthless bottles into a billion-dollar gold mine? Let's explore this cutting-edge recycling process in today's video. Each year, the world produces approximately 690 billion glass bottles and jars for the beverage, food, and pharmaceutical industries. Remarkably, glass is one of the few materials that can be recycled almost indefinitely without degradation. However, the reality is quite surprising. Despite its near-perfect recyclability, the world currently only recycles about 21% of the total amount of glass produced each year. A portion of those tens of millions of tons of collected glass doesn't end up as new bottles. Instead, it's used in a specialized industry called foam glass. Foam glass is non-flammable, non-absorbent, mold-resistant, insect-resistant, and can operate in harsh environments, from ultra-deep freeze storage to massive chemical plants. Like many other recycling industries, the production of foam glass begins with collecting pieces of glass that have completed their life cycle. This glass comes from various sources. These could be used beverage bottles, discarded food containers, flat panes of glass from old windows and buildings, or construction glass generated during demolition. After collection, they are transported to recycling centers via a widespread material recovery network. Europe currently has one of the most developed glass collection and recycling systems in the world. Here, millions of tons of waste glass are recovered each year instead of being landfilled. A portion of this is recycled into new bottles and containers. The rest embarks on a completely different journey to become foam glass. After arriving at the factory, the glass passes through a series of automated devices designed to remove impurities at a rate of tens of tons per hour. First, the material is poured into receiving hoppers and passed through an industrial vibrating screen. Particles that are too small, dust, and sand are separated at this stage. Next, a conveyor belt carries the material through high-powered magnets to remove nails, steel wire, metal caps, and other ferrous materials. Then, an eddy current separator system further removes non-ferrous metals such as aluminum. Once most of the metal has been removed, the glass enters the optical sorting area. Here, high-speed cameras and infrared sensors continuously scan each piece of material on the conveyor belt. The system can identify clear glass, amber glass, green glass, and detect any remaining ceramics, stone, and plastic. In just a few milliseconds, compressed air nozzles precisely blow each unwanted object out of the product stream. Thanks to this process, the purity of the glass after sorting can reach over 99.7% before being sent to the crushing stage. After being cleaned and sorted, the glass is further crushed into a suitable size. Depending on the production line design and the quality of the raw materials, manufacturers may use hammer mills or ball mills at this stage. For large pieces of glass from bottles or building glass, hammer mills are often used to quickly break the material into smaller particles. Meanwhile, some factories use ball mills to further finely grind or directly produce fine glass powder. Inside the giant grinding chambers, thousands of steel balls continuously impact the material until the desired size is reached. Depending on the required fineness, the grinding process can take from about 1 to 3 hours. The ultimate goal is to produce cullets or glass powder with a uniform particle size. Despite undergoing initial sorting, glass powder must pass another rigorous inspection before being fed into the furnace. Here, the material passes through multi-layered vibrating screens to remove particles that are too large or too small, ensuring uniform particle size throughout the entire production batch. After the screening stage, optical sensors scan the material stream at high speed to detect any remaining impurities, such as ceramics, stones, or materials with unusual colors. Simultaneously, metal detectors inspect each stream of material to remove tiny metal fragments that magnets or previous separation systems might have missed. After achieving the required purity, the glass powder is mixed with the most important ingredient of the entire process, foaming agent. Although it accounts for a very small proportion, usually only about 0.4 to 0.6% of the mixture volume, this is the deciding factor in whether the final product becomes foam glass or not. Manufacturers often use carbon powder or ultra-finely ground coke powder as a foaming agent. When the mixture is heated in the furnace, these carbon particles react and release gas right inside the softening glass mass. The formed air bubbles will be trapped in the material, creating millions of closed air cells distributed throughout the foam glass structure. Before entering the kiln, the mixture of glass powder and foaming agent must be carefully prepared to ensure uniform expansion. In many factories, a small amount of water, typically 5 to 10% by weight, is added to the mixture before it is passed through a wet rolling process. Continuously rotating rollers help distribute the moisture and foaming agent evenly throughout the material, while also breaking up any clumps that may have formed during mixing. The mixture is then spread into a uniform layer on a conveyor belt or heat-resistant tray. Depending on the product type, this layer is typically 1.5 to 5 inches thick before entering the kiln. After preparation and spreading, the material is placed in a continuous furnace, where a decisive transformation takes place from glass powder into a completely new material. Inside the furnace, the temperature gradually rises to approximately 1,700 degrees Fahrenheit. At this temperature, the glass particles do not completely melt but become soft and viscous, like a thick mass of honey slowly flowing out. Simultaneously, pre-mixed carbon or coke particles begin to react and release CO2 and other gases within the material. While the glass is in this soft state, these gas bubbles cannot escape. Instead, they are trapped within the material and gradually expand, forming millions of closed air pockets distributed throughout the structure. The entire foaming cycle typically lasts about 45 to 60 minutes. During this time, the temperature must be controlled with extreme precision. Upon exiting the furnace, the material has expanded many times its original volume. The result is a complete foam glass block containing millions of sealed air cells inside. This finished product is significantly lighter than conventional concrete, but is still strong and durable enough to serve in industrial constructions requiring a lifespan of decades. When it leaves the furnace, foam glass doesn't appear as small, finished sheets. Instead, it's a large block of material that continuously moves along the production line. Interestingly, many factories don't use saws or cutters to shape the product as they do with wood, plastic, or concrete. After it cools to the appropriate temperature, a mechanical vibration system transmits controlled vibrations into the material. Under the influence of these vibrations, the foam glass block separates along predetermined paths. This method creates blocks or sheets of very uniform size without the need for high-powered cutting blades. At the same time, it reduces dust generation and minimizes material waste. After completing the final quality control steps, foam glass is prepared for shipment to construction sites and customers worldwide. The blocks or sheets of material are first wrapped in polyethylene film to protect them from dust and moisture during storage and transport. Many types of packaging also incorporate UV protection to limit degradation of the packaging layer when stored outdoors for extended periods. Next, the product is labeled with complete information on dimensions, density, production batch, and technical specifications. The packages are then stacked on pallets, secured with straps and shrink wrap before being loaded into containers or trucks. From here, the foam glass begins its journey to construction sites, industrial plants, and infrastructure projects around the world. Leaving the factory, foam glass begins a new journey in the harshest environments that insulation materials face. Thanks to its fire resistance, water resistance, and long-lasting durability, it is used in many different fields, from civil construction to large-scale industrial projects. In the construction industry, foam glass is often installed on roofs, inside insulation walls, and in basements to reduce energy loss while preventing moisture from entering the building. Its non-absorbent properties allow the material to maintain stable performance for decades without decaying or deteriorating. In the industrial sector, foam glass is also found in chemical plants, power plants, and industrial cold storage systems. One of its most important applications is insulating LNG pipelines and liquefied gas storage tanks operating at extremely low temperatures, where many conventional materials cannot maintain long-term performance. In addition, foam glass aggregate is also used under industrial foundations, roads, and heavy-duty structures. Thanks to its structure containing millions of closed air cells, this material is significantly lighter than many traditional materials, yet durable enough to serve in structures with a lifespan of decades or even longer. Looking back at the entire journey, it's hard to believe that a material used in LNG plants, power plants, and modern buildings started from seemingly discarded bottles and glass shards. From collection, sorting, and grinding to foaming at temperatures close to 1,800 degrees Fahrenheit, each step is meticulously controlled to create a material that is both lightweight, durable, and possesses superior thermal insulation properties. What makes foam glass special is not only its manufacturing technology, but also its ability to give a new life to millions of tons of discarded glass each year. Instead of ending up in landfills, these glass shards are transformed into a material that can serve construction projects for decades. If you found this journey interesting, let us know your thoughts in the comments below. Don't forget to like and subscribe to discover more fascinating stories behind the materials and technologies we encounter in our daily lives.